Welcome to the Walton Pi. Today we're going to go through this problem from complex analysis. So we're going to show that if the sum of the modulus of an squared converges and none of the an's are -1, then the product of 1 plus an is going to converge to a non-zero limit if and only if the sum of an converges. And then we are going to, after that, find an example where the product of 1 plus an converges and the sum of an diverges. But notice that this does not have quite as many hypotheses as the starting. So this is going to show why some of those hypotheses are necessary. Now, before we get going, if you haven't already, please consider liking and subscribing. It really helps me to keep making these videos. And if you really liked it, please share it with some of your friends or comment down below what other types of things you would like to see me do. So, to do this problem, we are going to first establish a little lemma. So we're going to say, we're going to use the lemma that if the modulus of z is less than or equal to 1/2, then we are going to say that the absolute value of log of 1 plus z minus z is going to be less than or equal to some constant times the modulus of z squared. Now, why do we think that this is going to be helpful? Well, the product of 1 plus an, this is equal to e to the sum of the logarithms of 1 plus an. So this tells us that if the sum converges to some finite number, then the product will converge to some finite number. So hopefully there's some sort of connection there. So that's why we are caring about this particular function. So let's go through and show that this is going to be the case. Well, we know that the absolute value of log of 1 plus z minus z, that this is equal to the absolute value of the sum from k equals 1 to infinity of -1 to the k plus 1 z to the k divided by k minus z. Now, this is why we needed the modulus of z to be less than 1/2, so that it was within the interval of convergence of this series approximation of the logarithm. So that's why we needed the absolute value of z to be less than or equal to 1/2. You could have picked other things that also would have worked within the radius of convergence, which for this series is 1. But what we can do here is this then tells us that this is just equal to the modulus of the sum from k equals 2 to infinity of -1 to the k plus 1 z to the k divided by k, because there is a plus z and a minus z that cancel each other out, and this is equal to this is something times z squareds in every single term, so it means we can factor that out. So this is big O of z squared, which if you don't know what that means, that is precisely what is needed for it to be absolute value of c times the absolute value of z squared. So there we go. We can use that anytime we need it. So now let's go through our proof. So we are going to suppose that the sum of an squareds converges, and then we are going to so let's just start with that. So we are going to say that the sum of the absolute value of an's squareds converges. So let's actually just give that what that equals. Let's just say that that equals some value d. So it's going to converge, and none of the an's are -1. Now what we are going to do is we are going to assume, so we're going to do the reverse direction first. So we are going to assume that the sum of an's is going to converge. So we're going to say that that is equal to a, which is less than infinity. Okay. So now what this means is then there exists some value n where for all little n's bigger than big N, modulus of a sub little n is less than 1/2. And so we are going to just say, well, all the things before that are a finite number, so we can just ignore that piece. So we're going to say, assume without loss of generality that all a sub n's are less than 1/2. So without loss of generality, modulus of all is less than 1/2. Now what are we going to do with this? Well, now what we have is we have our previous lemma. So that means that we know that, so by lemma, we know that the absolute value of log of 1 plus z minus z is less than or equal to c modulus of z squared. So here we go. We got that. So now what does this mean? This means that if we were to look at the sums, the difference of sums, that means that the sum of the logs minus the sum of the z's is equal to c times the sum of the modulus of z squareds. Each of these z's were actually just one of those n's. So what we get is 1 plus an, an, an. So the sum of the logs is equal to some constant times the sum of our absolute value an squareds plus the sum of our an's, which is c times d plus a, which is some finite number. So therefore the sum of the logarithms converges, which we showed earlier means that the product converges. So the product of our 1 plus an's, this is equal to e to the sum of our logarithms of 1 plus an's. So this is going to be equal to e to the cd plus a, which is finite. And since none of the an's were 0, we don't have any of the logarithm pieces going to 0, and e to anything is not going to be 0, so we're going to be good. Now let's go and do the forward direction. Now the forward direction is going to be very, very similar. We're going to start by saying that the product of 1 plus an's is equal to some finite number. Let's call it, in this case, c. And then what we are going to say, and that is not 0. So then what we are going to do is we are going to be going through and saying, well, because it's not equal to 0, we can do e to the log of that. So then that means this is c equals e to the sum of the logarithms of the 1 plus an's. And so here's where we're going to then do pretty much the justification we had right here. By this same logic, we can then replace that with stuff that we know and stuff we don't, and we can go through and solve for that. And that's going to give us the exact same sort of thing, just sort of in a reverse order. So for the same sort of reason, we can say, well, we can go through all of that same process, and we are going to be able to get that. So here we go. So this is equal to the log of c. So that means that log of c equals the sum of the logs of 1 plus an's, which is equal to the sum of the an squareds plus the sum of the an's. So that means the sum of an's is equal to log c d, which is a finite number, and there we go. In both cases, we were able to get a finite number, and so both of them were going to work in both cases. Now let's go and look at our example of something that shows why we need all of those different conditions. So find an example where the product converges, sum diverges. Now notice it just says the product converges. It doesn't say it converges to a non-zero limit. So let's just find a product that's going to go to 0. Well, the product of 1/2 every time, that's going to 0. So let's say that a sub n is equal to a negative 1/2 every single time. And so then what we have is we have the product of 1 minus 1/2. That goes to 0. But the sum of negative 1/2, that goes to negative infinity. And so we have the sum diverge, but the product is going to converge. And so that is how you would go through and do this problem. If this was helpful, please like and subscribe, check out some of my other videos, and please let me know what other types of problems you would like to see me do. I hope you have a great rest of your day, and good luck with all of your math.